Good morning. My name is Ankush Chakrabarty, and I'm a research scientist at Mitsubishi Electric Research Labs. Today, I'm going to be talking about using Bayesian optimization for calibrating buildings with joint dynamics for both building envelope as well as HVAC systems. And this is joint work with Emilio Maddalena at EPFL Switzerland, as well as Chris Lockman and Hongtao Chow at Merck. Thank you for joining us. We know that physics-informed simulation models of HVAC and buildings play a critical role in analysis, control, and optimization of building systems. For example, in model predictive control. The prediction quality, however, is strongly linked to how well these models have been calibrated, or how good a set of parameters we have for these models and how well they reflect the true system dynamics. And even though one may argue that some of the parameter values are known during the building's construction, the truth is that they can change quite a lot from the blueprint after construction. And so it's necessary to re-estimate them. Other coefficients, such as heat exchanger coefficients, may need to be directly estimated from measured data. So in this paper, we're trying to find the parameter values that most accurately represent observed data using systematic data-driven algorithms by optimizing a particular calibration cost, which is user-defined. An example of such a cost is the coefficient of variation of root mean squared error. In this work, we explicitly consider both the HVAC dynamics as well as the building dynamics. And the reason for that will be made clear through this figure here. So this is a sparsity pattern of the state matrix of a linearized HVAC plus building system. So we see both the HVAC states and the building states, but more importantly, we see that there are coupled states. So there is coupling between these two subsystems. And actually the value of the elements of these coupled states is not small at all. So there's a lot of information that could be exploited from the coupling that is largely ignored in the previous literature. However, this comes at a cost. So adding the HVAC means you're increasing model complexity and typically increasing numerical stiffness. And in fact, an eigenvalue analysis of this matrix will show that the time constants of these dynamics range from milliseconds all the way up to days. So it's very slow to simulate this system typically. There's also more parameters to estimate because the HVAC subsystem is in there explicitly. And oftentimes, software modules like Modelica and Energy Plus may have very well-defined, well-optimized code, but it's hard to read the equations because they're hidden underneath the code. So typically closed-form solutions or closed-form even representations of the system are unwieldy and difficult to use, and gradient-based methods don't always work very well. So in this paper, we're looking at Bayesian optimization, which is a probabilistic machine learning algorithm which can calibrate models without requiring too many simulations. And also, it can perform in a completely data-driven manner. In fact, it's model agnostic, so it doesn't even need to know what the closed form representation of these models are. As many of us are aware, Bayesian methods have already shown very good performance in the building calibration problem. However, the wealth of the literature that exists in Bayesian methods for calibration is typically different from the way that we are implementing Bayesian optimization. In particular, Bayesian calibration builds or generates statistical models of the dynamics of the system, or meta models of the dynamics across the whole state parameter space. And by doing so, they have not only model of how the parameter changes the system dynamics, but they can also predict the state itself. However, in Bayesian optimization, we rely directly on the high fidelity model, such as a Modelica model or an Energy Plus model, in order to give us state updates. And instead, we are learning only a map from the parameters to the calibration cost. And typically, this learner has to solve a simpler task than what Bayesian calibration has to do, because we're learning a simpler problem, just learning what a cost function looks like based on data. Secondly, Bayesian calibration is somewhat open loop, which means that once you know a prior distribution on your parameter space, you can then sample off of that distribution without requiring consecutive updates to the prior. Whereas Bayesian optimization is kind of a feedback-based or a closed-loop approach, where the next sample location is going to be decided by all of the information you have so far. And this is why typically it requires fewer iterations of Bayesian optimization to converge compared to Monte Carlo type methods that are more prevalent in Bayesian calibration approaches. So this figure is a very typical workflow of data-driven model calibration using Bayesian optimization-like methods. So from the top left, we have a building and HVAC system from which we assume that we are getting some measured data. We also assume we have a digital twin or a software simulator from which we can generate the same signals, the same output signals as the measurements that we have, for example, temperatures, given a particular parameter for that model, parameter set for that model. Based on the data and the outputs, we can compute some calibration cost function. And since the parameter to calibration cost is an unknown function, we use probabilistic learning in Bayesian optimization to approximate what the parameter to calibration cost function looks like. And we do so with Gaussian process regression. And from Gaussian process regression, we can extract statistical information and other information, theoretic measures, to understand what are the most likely regions in the parameter space to contain the optimal set of parameters for this simulation model. And iteratively, we can estimate candidate parameter sets that will converge to the optimum under a very standard assumption. We do assume that we have some range for these parameters, such as a lower upper limit or bound, but we don't assume that we have any prior distributions, which is the difference from traditional Bayesian calibration methods. Just so we're all on the same page, let me go through the terminology for Bayesian optimization. We assume that we have an unknown function, f of x, that we want to minimize. By unknown, we mean that we can evaluate this model. So if you give me an x, I can give you an fx, but I don't know what it looks like over all of x. And I can't take gradients because I don't have a simple or a closed form representation of this function, which is exactly the case in the build calibration problem. So the two main pieces of Bayesian optimization are the Gaussian process, which is a way of doing probabilistic regression, where if you've seen some parameters before and you know the cost associated with those parameters, you can use that information to model the entire function over the entire admissible set of parameters with uncertainty quantification. So you can get closed form marginal means and variances. And based off of the Gaussian process, one can construct acquisition functions, which trades off the exploration and exploitation. So it wants to explore the areas which have large variance, because that's where the function is most uncertain, but it also wants to exploit the information that it's seen so far. So in a minimization problem, it might want to evaluate the model at a parameter set where there's very likely to be a very low mean value based on the GP. So the acquisition function trades off the exploration and exploitation automatically through the GP's statistics. Here's an example of Bayesian optimization for maximization, actually. The top plot shows the real function in the continuous black line. And you can see the sort of narrower black line is the mean of the Gaussian process. And you'll see that the uncertainty bands are starting to constrict around the areas that you've seen data, and is initially wider apart because we haven't seen a lot of the function, but more and more data, they become tighter and tighter around the true function. The acquisition function, there's a few of them here, but initially they're exploring, so they want to search in areas where the function has high uncertainty. And later they're tightening around where there actually is a maximum for the true function. We've already established that the major workhorse of learning in Bayesian optimization is the Gaussian process. But a major problem with Gaussian process is that it doesn't scale well with the number of data points or the number of dimensions of the problem. In fact, it exhibits cubic growth in the number of data points, which means it's really ineffective when you have more than, say, 2,000 or 3,000 data points or 2,000 or 3,000 model evaluations. And even though I said at the start of the talk that we're trying to minimize the number of model evaluations, if we have a system or a simulation model with a lot of parameters, say hundreds of parameters, it is unreasonable to expect that you will be able to solve this problem without at least some thousands of model simulations, because it's such a large dimensional space. So one major technical contribution of this work is to move away from Gaussian processes towards sparse Gaussian processes, or SGPs. And SGPs have been studied and are well known that they lower the computational burden of GPs by essentially replacing the entire data set that you've seen so far with a few representative points that kind of cover the data very well. And these representative points are called pseudo inputs or inducing points. This allows us to scale our calibration strategy to multiple parameters. In fact, we have an example showing 17 parameters simultaneously being calibrated. An example of how SGP does is kind of shown on the right here, where if you look at a one-dimensional function and an exact GP with 300 data points, then even with 30 well-chosen inducing points, the SGP actually replaces the initial data set and reproduces the function that the exact GP is showing with pretty good accuracy. We performed the calibration task via simulations in Modelica. We used a lumped parameter heat exchanger models for fast simulations. As a reference, typical finite volume methods use about 1200 to 1300 seconds for the simulation we do, whereas with the lump parameters, we can do it in 14 seconds. So that's 2 orders of magnitude speed up. The Modelica cycle and Modelica building are connected through the Modelica buildings library, and we describe this one zone single family house shown in the bottom right here, and the cycle model is shown in the bottom middle here. We use ambient conditions from a TMY3 file based in Atlanta, USA, that you can see some of the ambient temperature, relative humidity, and irradiance variations over a couple of weeks on the top right here. And we do a integrated system simulation of 2 weeks in about 42 to 60 seconds, depending on parameters and initial conditions. Our calibration task involved trying to estimate 17 parameters, 9 of which are building, the rest are HVAC. We have a training set built from data collected every 15 minutes in the first 2 weeks of July. And then July 15th all the way to September 14th is when we test that data using our model, our calibrated model. And the bottom left table shows that the output errors using the calibrated model are all within ASHRAE limits for a variety of outputs, such as temperatures, humidities, suction, superheat, compressor frequency, etc. So both HVAC and building outputs. And in most cases, it's actually very accurate, so over 99.9% accurate. Now we understand that this was because our simulated outputs and our simulation model was very representative of the true model, because the true data was collected also from the same simulated model, and likely these numbers will change with real data, but these results are encouraging nevertheless. What is more encouraging perhaps is that when we tested this on building energy or power, we also had very accurate estimates of the power of the building, as you can see from this right plots here. So the CVR/MSE from building power was less than 10%, despite this being a completely out of training set signal, which means that we did not use the building energy or power as a measured output for the model. Instead, we calibrated the model and used the prediction of different components, which are power heavy, and we still get very good estimates of the total building and cycle power. This table shows the parameters that we were calibrating. So on the building side, we have, for example, infiltration rate of the airflow, solar emissivity coefficients, room air heat transfer coefficients, and thicknesses such as building material properties. And for the HVAC side, we have mostly heat exchanger, heat transfer coefficients that we're trying to estimate. All of these parameters were selected to have varying levels of sensitivity with respect to the measured outputs, so that the problem is not trivial to solve. The uncertainty bounds on these parameters are non-trivial as well. They're plus minus 15% for all the parameters. And the true values, of course, are hidden during the calibration process. But the true data that was produced here was indeed from the simulation model that is being calibrated. And we can see that 13 out of the 17 parameters that we're calibrating can indeed be estimated very accurately with over 90% accuracy, even though we only use 750 iterations to do this. So this is why Bayesian optimization is greatly advantageous. It does not require a lot of model evaluations, even though it can end up with a very good estimate of the parameters. So a lot of prior art in building calibration requires either a good initial set of parameters, for example, in gradient-based methods, or in MCMC type methods or Bayesian calibration methods require good prior distribution over the parameters to be calibrated. A very big advantage of Bayesian optimization is that it has an initial sort of random exploration phase guided by the acquisition function. So actually it should be, or is expected to be, pretty immune to the initial set of parameters. So it doesn't need a good initial guess. And this is evident from these box plots here. So we show for all of the 17 parameters over 20 random initial guesses that the estimates are pretty tight, and these stars show the true parameter value, and the box plots are the statistics from the 20 runs. And in all cases, the median of the box plots are very close to the true values, and the uncertainties over the 20 runs are pretty tight around the true value as well. So this method is indeed robust to the initial set of parameters. To summarize, we've developed a scalable Bayesian optimization methodology for calibrating buildings and HVAC models in an integrated way, using only data without requiring model information by exploiting probabilistic machine learning. We propose sparse GPs as a scalable alternative to GPs in Bayesian optimization as meta models for the calibration cost function, rather than learning the more complicated state dynamics as a meta model. We showed over 90% accuracy on 13 out of 17 parameters learned concurrently. We showed that the outputs we estimate are within ASHRAE limits in simulation. And we also demonstrated the method is robust to the initial guess or initial set of samples used to construct the sparse GP model. In the future, we plan to test this method on realistic data and real experiments, which will be more noisy and will have larger model mismatch. Thank you for listening.